Okay, we are starting this revision of quantum physics. It's a part of modern physics. The first, sorry, is an introduction. There are two main branches of physics. One is called modern physics, and second is called conventional physics. So there is a contrast between modern physics and conventional physics. And the first was the Einstein work, and the previous one was the Newton work. We remember that there are two defined characters in our knowledge. One is called particle character, which is coming from the mass, and second is the wave character, that is due to energy. Now, the two characters, one is particle character and second is wave character. Mass, momentum, pressure are typical particle character. Wave character are energy, wavelength, and frequency. Now we talk about quanta. What is quanta? Quanta is a name for the packet of energy. Quanta is a packet of energy, and we have a concept that energy is quantized. Energy of a quanta is directly proportional to frequency. This is the new physics selected this idea that energy is a character of frequency. That is why the famous concept established, that is the concept of Planck constant. The unit of Planck constant is this: V is equal to F lambda, F is equal to C upon lambda, and you can see E is equal to HC upon lambda. Now, energy transferred by a wave. In conventional physics, it is the amplitude, and in modern physics, it is the frequency. Wave particle duality, what is this? This is a very famous theory. Wave particle duality says that every wave has a particle character and every particle has a wave character. At a time, only one character is dominant, so both characters are not visible simultaneously. What is a photon? Photon is a Photon is a quantum of electromagnetic radiation. Now, the core topic, photoelectric effect. What is photoelectric effect? When a high frequency electromagnetic radiation strikes a metal surface, it releases electron. This is a metal plate. High frequency radiation hits, electrons are emitted. This is called Now, this is called photoelectric effect. This is called photoelectric effect. And there, the high energy electrons are emitting. Photoelectric effect. The most. This is the threshold frequency is required. Okay. And the photocell is the biggest application of it. So a cell which generates electric current, this is a photocell. High energy electrons are emitted from that. Now we have some important terms in photoelectric effect: threshold frequency, work function, instantaneous emission, concept of maximum EK, photoelectric equation, stopping potential. What is threshold frequency? It is the minimum frequency at which photoelectric effect will start. It is the minimum frequency at which photoelectric effect will start, and before that, below this frequency, electrons are not emitted. So this is a cutoff position for this. Now, when frequency of radiation is less than this number, photoelectric effect does not start. It's a very important sketch. Energy on y-axis and frequency on x-axis. So we have a threshold frequency. This is a gradient is equal to E upon F. Now, F naught is x-intercept. This is the point where photoelectric effect starts. If you change the metal, photoelectric effect will not be affected until threshold is matching. Look, when you change the metal, photo threshold frequency has changed because different metals are reactive to different extent. So for P, most reactive, and for this one is the, what is work function? Work function is the minimum energy required to eject electron from the surface of a metal. Now here is the metal surface, electromagnetic wave hits the surface of the metal, electrons are ejected. The formula for work function, look at the formula. The formula for work function is this: phi is equal to HF naught. Now, phi is a character of the metal. For reactive metal, work function is less and reverse also occur. So this is the threshold, this is the cutoff position, and this is called work function. Instantaneous emission, if the incident frequency if the incident frequency is equal or greater than the threshold frequency, electrons begin to eject immediately. So electron emission is instantaneous. What is the contribution of intensity? Intensity is a measure of power per unit area. So intensity of illumination is actually proportional to the photoelectric current. So look at this. Now, if you increase intensity, you will get more photons with the same energy. So intensity is increased. Remember, one photon can eject only one electron. That is why if the frequency exceeds, the threshold, photoelectric effect will start. If you increase the intensity, you will get more current. If the incident frequency is less than threshold, no photoelectric effect will occur. Contribution of frequency. Contribution of frequency, when you increase frequency, you will get the same number of photons with greater energy. So look at this idea that one photon, one electron, frequency is increased, you will get more energy with the same photon. Maximum photoelectric energy is independent to intensity. It doesn't matter how much intense is the light, but photoelectric energy depends upon frequency. One photon, one electron. It means when the photon hits an electron, it will eject only one photon, only one electron, just like a football on the ground, and you kick it. So you can eject one kick. You can eject the football. So Einstein was the first person who suggested this concept. Concept of maximum EK. When the electron is hit by a photon on the surface of the metal, electron comes out, overcome the resistance using the work function, reaches the ejection point, and then kinetic energy is transferred. First energy part is always gone to work function. Remaining energy is always transferred. Whatever left behind will become kinetic energy. That is why it is called maximum kinetic energy. Now, if the electron is below the surface, it is first brought up to the surface and then it can be ejected. Photoelectric equation. There are two main versions, work function and energy. This is the reason. Now, this is called photoelectric equation. HF is equal to HF naught plus half mv squared. And normally, when you talk about this topic, this topic doesn't come very occasionally, but it is called stopping potential. What is stopping potential? Stopping potential is called the potential which stop the photoelectrons coming out. Then this is the graph. Look at the graph is horizontal on different intensities. Conclusion. Photoelectric effect provide evidence for particulate nature of electromagnetic radiation. Wave nature of particle. Particles can show wave character, and the most common example is diffraction in electrons. When a beam of electron is projected to a double slit type experiment, it produces a typical diffraction pattern. This diffraction pattern proves that electrons can behave like particles. De Broglie wavelength. This is a mathematical justification of this wave-particle duality. Now, he said that Einstein suggested that every particle has a particle wave character and every wave has a particle character. Now, look at this. We have E is equal to mc square and E is equal to hc upon lambda. When you equated it, you get a formula. Lambda is equal to h upon p. Lambda is equal to de Broglie wavelength. This is a sketch. Now, primary classification of spectra. There are two types of spectra, continuous and the line. Look, this is the continuous spectrum, no gap in between. And this is the line spectra. There are gaps between the energy lines. There are two types of line spectra, emission line spectra and absorption line spectrum. What is emission spectrum? Electrons are orbiting around the nucleus. They have their own energy levels. When a photon of high energy, suitable energy, hit an electron, electron will jump to a higher level. It will stop there for some time and then comes back. This is called excitation and then de-excitation. This is the case. So electron can jump from one level to another. Now electron is here. This is the K, L, M, N shell. An electron is struck by a photon. An electron will jump to a higher level, and then after staying there in the higher level, it comes back. It will not stay there forever. The electron will reach to the higher level if the energy of the photon is precisely equal to the energy difference of the two levels. Then there is a de-excitation and the electron comes back. We'll show it by this energy level diagram. Look, this is the energy difference. We use these type of calculations. And remember, delta E is equal to hc upon lambda. Common photons which cause this transition are ultraviolet, visible, and infrared. Downward arrows means energy is being released. The bigger jumps are by UV photon. We make a little spectrum below also. This is a little spectrum. From left side, it's a high frequency, and from right side, it is the lowest frequency. Now, downward arrows show de-excitation of electrons. Now this is called line spectrum. For every element, it is unique. For every element, it is unique. Now, what is absorption spectrum? Look, when the spectrum is constituted by the frequencies of light, light which is transmitted with dark bands. There are gaps in between, and these gaps are dark. We have a cylinder containing hydrogen gas, and the different wavelengths are coming. White light consists of different wavelengths. When the waves pass through, the hydrogen gas cylinder, some of the photons are absorbed and some of them continue to move. Now, after a short interval, the absorbed photons are re-emitted. And this causes this type of spectrum. Now look at this. There are dark lines here. These dark lines show what? Absorption spectrum. Absorption spectrum are actually the reason for the absorption of photon and re-emission. Now look at this. The arrows are upward and they are causing dark lines. In an absorption spectrum, arrows of transmission are upward. Look at this. Now, this is called an absorption spectrum example. Comparing spectra. So first is continuous, second is emission, third is absorption. What is the conclusion? A line spectrum is an evidence for the discrete nature of energy levels in an atom. So that's for this. This is all for the revision of this chapter.